So today we're going to talk about carbons by XPS. Now first I want to apologise, I can't be there in person today. I'm at a conference, but carbon is probably one of the most simplest, most ubiquitous and equally the most infuriating core levels sometimes to analyse. So here are some examples of carbon core level spectra that we see. On the left hand side we have the typical graphitic type carbon. This is taken from a HOPG sample, so probably the most perfect graphitic type sample that you can get. And we can see it has a certain characteristics, shapes, which we will come on to slightly later on in this little overview. We can also have materials such as graphene oxide, which has a series of oxidized species on the surface of the graphitic carbon. And indeed we can also have reduced graphene oxide, which takes such graphene oxide and reduces it back to a graphitic state, but retaining sometimes a lot of the oxygenated functionalities. We can also have the more common, if we work with things like metal oxides or just any typical sample which has been introduced into the XPS system from the atmosphere, adventitious, or the so-called adventitious type carbon. Now we can choose to fit or not fit the spectra. It all depends on what we want to achieve, but hopefully over the next few slides you'll be able to see some of the power that we can have from, or information we can get from, carbon 1s spectra, and indeed hopefully give you some way to understanding on how to approach different carbon materials. So some other examples of carbon core level spectra. I just thought I'd include these because again it covers a wide range of materials. Again we have the HOPG sample here. Going from the other end of the spectrum, from a fully SP2 system as we would have in HOPG to a virtually fully SP3 system here with diamond, and we can see the difference in shapes between these two core level spectra. Even though it's still carbon, we obviously the characteristics, the electronic properties and so forth greatly influence what we see in our spectra. If we hydrogenate or oxidize a graphitic carbon, we can see significant changes to the material and the shape of the spectrum if we compare this one to our HOPG sample. And indeed if we start fluorinating or greater degrees of oxidation or hydrogenation, we can see significant changes again in the core level spectra over that of a simply oxidized or minimally oxidized sample over graphitic carbon as well. So we'll start with adventitious carbon. As I say, this doesn't generally need to be fitted, although it is useful to fit the data to get a more accurate assignment of the carbon peak for charge compensation, for example. There are a few caveats with that, which we will cover in some of the upcoming slides, but what I want you to notice is, or take home, is you don't necessarily have to fit this, but it can give you information on the surface speciation or anything that's going on your surface. I want to point out this paper by Mark Basinger in Applied Surface Science, talking about using the carbon 1s for charge correction. Now some of you may have seen a lot of debate in the literature in terms of carbon being a poor charge reference point, and that has been known for the last 30 plus years in XPS. However, it is convenient and it is useful, and what we talk about in XPS is typically relative shifts. So actually what you can find is, and this, as Mark points out in his paper, that taking a adventitious carbon of a binding energy to be 284.8 electron volts typically has a standard deviation of about 0.25 electron volts, so well within our experimental uncertainty. Now, full width half maxima of each peak when you come to fitting tends to depend on the resolution of your system. So very roughly speaking, if you take a Kratos, Axis Ultra or Axis Supra type system, then about 20 EV pass NG, you will have the full width half maximum of these peaks, generally somewhere in the region of about 1.2 to 1.5 electron volts. Of course, this does depend on if it's a slight degree of charging, degree of oxidation, or how much carbon is on the surface and so forth, but this gives you some idea of what you might find. Generally, the line shape tends to be a Gaussian-Lorentzian type blend, and personally I just use this LA 1.53,243 line shape. It certainly works better than a standard GL30, which you might encounter with some XPS installations or libraries. Whilst they will give very similar results, a Lorentzian or asymmetric Lorentzian, which is what the LA part of this line shape refers to, is much less sensitive to deviations in noise than just a simple Gaussian-Lorentzian blend, as is the GL30. We have to take care, however, about the assignment of this carbon-carbon or carbon-hydrogen peak. If there's significant changes in the chemistry of the surface, for example, you start getting graphitization from a reaction process, or the basicity of your surface changes, then it can have an influence on how this adventitious carbon interacts with the surface, and therefore can cause a shift. And this is indeed links back to that sort of uncertainty or debate that's come up again in the literature. So very roughly speaking, the peaks that we see here in this table are fitted equally here in this adventitious carbon spectra, and we can see that generally each peak is somewhere in the region of about 1.5 to 3 to 4 electron volts away from this 284.8 electron volts. Note we give the same full width half maximum constraints, and again we'll be able to see how we do that within XPS during the sort of hands-on session. Of course, some of these peaks may not appear in certain materials. For example, you may not see carbonate. Some materials, some metal oxides for example, certainly carbonize or form carbonates much easier than other metals, and so you may or may not see such a peak. So returning to that point about surface acidity or surface basicity, whichever way you want to look at it, we're going to take an example of an aluminosilicate, a zeolite material. And you can read more about this in applications of X-ray Photoelectron Spectroscopy to catalytic studies. In the chapter I wrote in chapter 5 in terms of charge compensation, charge calibration. But the key point I want to take here is we've taken the binding energy of 285 electron volts here for the carbon. There's slight charging on one of the materials, but what we're doing here is altering the silicon-aluminium ratio, and by changing that ratio we're changing the surface basicity or acidity, whichever way you want to look at it, at the zeolite surface. So if we align those carbons, what we can see is the aluminium component of the zeolite lines up beautifully. They all come at the same energy. Whereas if we look at the silicon 2p, there's almost a 1 electron volt shift, so a very significant shift. So we might wish to infer chemistry from that, but indeed we have to be careful. Again, if we flick this around and align on the silica peak, or the silicon 2p peak for the zeolite, we can see we have some shift now in the aluminium. And again, we have this 0.9 EV shift. Instead of being in the silicon this time, it is now in the carbon. And again, reversed or mirrored in the aluminium 2p. So we have to be very careful in terms of picking a alignment point. And as we said, although the controversy has been known for the last 30 years or so, we always need, if we're using carbon as a charge reference, a secondary reference point to make sure that it is a suitable reference point. Because we don't really expect a large, or certainly not an almost 1 electron volt change in the silicon binding energy when we have an aluminosilicate where the biggest component is the silicon on SiO2 type repeating units. Okay. So let's move on to graphitic carbons. So graphitic carbons typically characterized by a binding energy which we take to be 284.5 electron volts. Now, you will see values vary in the literature. The true binding energy for graphitic carbon, or HOPG, is probably 284.3 electron volts, but please use 284.5 as is consistent with 90+% of the literature. And again, our 0.2 is within our experimental uncertainty. Graphitic carbon is characterized by an asymmetric shape, which arises because that carbon is conducting. So we can see instead of this Gaussian, single Gaussian Lorentzian type peak, we do have asymmetry to the higher binding energy side, and then that leads into the shake-up satellites, and here we can see a blow-up of that structure, and we can see 1, 2, maybe an even small third peak, which are due to pi star shake-up transitions. And these arise because we have phenol rings, or these benzene rings, all in the lattice for the graphitic network, for the graphitic carbon, and of course electrons can be promoted from core level. Electrons can be promoted to unoccupied orbitals, and therefore this is an energy loss process. So some of the electrons coming out lose their kinetic energy, and therefore if you lose kinetic energy, you appear at the higher binding energy. And these can be quite diagnostic sometimes. What we must realise is this is part of the total graphitic carbon photoemission signal, because it steals that intensity from the main peak and therefore must be included in any sort of quantification. So that's all well and good, but we have to be careful when we talk about graphitic carbons, because not all graphitic carbons are equal. So here we have two spectra for look to be nominally the same material. Again, this is the survey spectrum, so we can see our carbon 1s core levels, energy loss processes, and a carbon Auger up here at the higher binding energy, low kinetic energy side. I've enlarged the oxygen 1s region from both spectra here as well, and we can see that these are void of oxygen. And again, we don't see an oxygen Auger at around about 960 electron volts binding energy, which will be characteristic of, or indeed show us that there is oxygen there. So both these materials are free of oxygen. So we might think that we can use a spectra that we might derive for HOPG to look at these so-called nano onions. But let's superimpose the spectra. Now these were run at the same pass energy, these were run under identical conditions, step size, pass energy, etc. on the same instrument, and what we can see is a difference in the spectra. Whilst they both come in at binding energy about 284.5 electron volts and have this pi to pi star structure as well, we can see that the nano onion spectra, displayed in the blue this time, is much broader, and indeed there's a slight difference in the positioning of the pi to pi star transitions as well. So what we can take from this is that HOPG is possibly not the best model for all graphitic carbons. However, it is a good base to understand changes in carbon spectra of graphite or graphitic materials in general. But what we want to take from this, and this is a structure, this is a TM image and a sort of graphical representation of what a nano onion is. So you can think of it as a buckyball within a buckyball within a buckyball, and so forth. But this raises some very interesting questions or points of note for the spectra. we have this greater asymmetry, we have a greater full width half maxima, and this is because there's essentially strain on the system. So the spectra itself is affected by the curvature of the carbon. Indeed, these nano onions we've talked about, and if we had single buckyballs, and indeed carbon nanotubes as well, be they single-walled, double-walled or multi-walled carbon nanotubes, will have some extra degree of width, slight extra asymmetry, and also some elongation to the lower binding energy side. And this all comes from strain, and some nice papers you can look at in the literature discussing that. And just to highlight that even further, here's the spectra again, acquired under all similar conditions for HOPG, nano onions, and multi-wall carbon nanotube. Again, the multi-wall did have a little bit of oxygen, but nevertheless, it gives you an idea. We can see that the multi-wall carbon nanotube fits the spectra of the nano onion much better than the HOPG does, especially at the lower binding energy side. And there we are, it's attributed to defects and strain in the material. Those who do synchrotron type experiments, I want you to note that the carbon 1s full width half maximum and the intensity of this satellite will vary as a function of photon energy. Think about you probing different depths. And this paper, if I recall, is the correct one to discussing these points. And that's some lovely work which came out of the Fritz Haber Institute and the Bessie light source. One useful thing when recording carbon spectra is to also record the carbon Auger. Carbon Augers, well, Augers in general, are very chemically diagnostic. Because they are a 3-electron process, the transitions that occur in that 3-electron process are dominated by changes which have happened in both initial and final state of the carbon material, or any material in general, if we're talking generically about Augers. But Blaskovich and Scaglione showed many years ago now that you could, if you record the X-ray induced carbon Auger spectra, and here it is in the kinetic energy. Auger spectra are normally recorded or presented in kinetic energy as opposed to binding energy. And then we can see that if you take the first differential of the carbon Auger for diamond and HOPG, we have significantly different values for the highest and the lowest points. And indeed, Blaskovich and Scaglione done this for a range of materials, range from diamond to HOPG, amorphous carbons, hydrogenated carbons, what they call as defective graphite, where they've sort of argon etched them slightly to introduce some defects. And they could correlate the amount of disorder or amount of damage, or if you like sp3 character within the sp2 of by a straight line agreement between a value of around about 13 to 14 to a value of around about 23 or so. So that's a nice way of being able to get some information on the amount of sp2 content in the material. I just want to point out, we think carbon has been pretty inert perhaps. But what we can do is, depending on the type of graphitic material that you're looking at, they can actually be damaged by your analysis. So for example, let's take graphene oxide. So this is a commercial graphene oxide. And if we continuously analyse this, then what we can see is a reduction of this peak at around about 288 electron volts, with a concomitant increase of the peak around about 285 or so electron volts. And we can see that the colour code in here, the purpley colour is at the start, going through to these sort of greeny colours in the 100th scan, and we can see the green coming up here and decreasing there. Now this is very similar to degradation observed for polymers, so you have to think about how you perform experiments on things like graphene oxide, what system you're looking at, how long you scan for, and so forth. And of course this degradation, this change, as we can see, there's subtle changes in the positioning of the data, so we can't typically get absolute binding energies unless we record the data in the correct way. But this will also have an effect on the oxygen to carbon ratio when we look at these materials, which may be important to us if we've taken a graphitic oxide or a graphitic carbon and oxidized or done some treatment to try and introduce more function, change a function, or whatever. And again, we can see that this change is concomitant again. The changes in the carbon we can relate back to the changes in the oxygen 1s spectra. And this is an important thing. Although we will be looking hands-on with only the carbon spectra in this case, you have to take XPS spectra as a whole. And indeed, the carbon changes in the carbon 1s should be reflected by changes in the oxygen as well, if these two elements are linked, which typically in carbonaceous materials they are. So again, another thing to point out is how you prepare your samples for XPS analysis. So this is a functionalized fuel-layered graphene powder, and we've looked at this in two ways. We've just looked at the powder straight from the pot, and we've also pelletized it. And this work, I should point out, has been done in conjunction with BAM and MPL, and you can read this in Carbon. But basically, what we can see from just a cursory look at the carbon 1s and the equivalent oxygen 1s spectra for the pelletized on the top and the powder on the bottom is the spectra look very similar. But when you look a little bit more closely, then what you can see is that there are changes in this area around about above, well, predominantly you can see it here, but again you can see the changes from 285 electron volts upwards. And if we look at the oxygen to carbon ratio, we have 0.1 here and 0.2, so 0.2 for the powder and 0.1 for the pelletized. Now that doesn't sound like a big difference, but we can see that pelletizing, these have been compressed and there's something around about 1.5 to 2 tons of pressure for carbon. It's had a notable effect on the spectra. So we have to think about how we look at these materials and be consistent in the way that we mount our samples for analysis. One thing the paper didn't mention is if you take these powders, and again this is a bit more information on, this is the paper, the Laskovich and Scaglione paper that I mentioned earlier on. If you look at the powder versus the pelletized, then when you look at the powder, it gives a D parameter of 21. So if we read off that table, we have around about 80% sp2. So we have 20% or thereabouts of sp3-like material in this compressed powder, in the loose powder. When we compress it, we get a D parameter of 24. Now slightly higher than the HOPG value of 22.5, which was reported by Scaglione. But typically, anywhere we often see on systems a value of between 23 and 24 for pure or very highly orientated graphitic carbons. And these are typically plus or minus 1 electron volt anyway. So these values that we derive here, the full width half maximum, is just the difference between the highest and the lowest points, and these values tend to be, or the uncertainty in these values tend to be the uncertainty in your step size, and these are typically recorded at 0.5 to 1 electron volt step size, just for quickness. So we've addressed some of the points. Here are some useful references in terms of carbonaceous materials. So the first is a paper by myself talking about XPS analysis of carbon materials. This is open access. There's a lovely set of practical guides for XPS, and there's one on interpreting the carbon 1s spectrum by Matt Linford and co-workers. That's a very interesting one to read because you can see the differences in how line shapes can affect quantification, and indeed how subtle changes in the background can influence the spectra as well. This is the paper by Mark Basinger in terms of adventitious carbon referencing, and indeed this is one which again was done partly with the National Facility, myself and Neil Fairley of Casa XPS fame, and indeed talks about using a Doniot-Sunjic type Shirley combined peak shape for fitting asymmetric signals for graphene oxide materials. This is a little bit more advanced, but very useful nevertheless to understand carbon spectra. So what I want everybody to have a little go at now is just start playing around with whatever you feel you want to tackle. So first of all, you'll have two VAMUS files, one called carbons and one called D parameter. The carbon contains all the carbon 1s spectra for different species, and what I want you to do is look at the adventitious carbon spectra. How many peaks do you need? Does it tell you anything? Have a think and discussion about what does it tell you about the surface. I want you to compare peak model for fitting graphitic carbon, use the HOPG, including the pi star structure. I want you to compare that to the model that is in reference 2 on the previous slide. So that's the Matt Linford paper that I mentioned. What are your thoughts on the two models? Have a discussion between yourselves or with the demonstrators. Once you have a suitable model, or what you feel is a suitable model for the HOPG, take that model and copy and paste it into the nano onion spectra. Does it fit? Do you need to make any changes? Why are you making those changes, and what changes are you making? What does the spectra itself tell us about the nano onion? Think about what we've already said in terms of discussing these sort of curved species. I also want you to have a little look at the D parameter spectra, and there are videos for these as well to just show you quickly on methodologies on how to quickly get this data.